So in this lecture, we're going to talk about piezoelectric transduction. It's another transduction mechanism that is gaining more and more, let's say, momentum at microscales, and that's because of the advancements they have had in processing technologies over the past few years. Now you have a lot of different devices that actually have a piezoelectric interface for the, let's say, between the mechanical domain and electrical domain. Nowadays we have resonators made this way, and also microphones and vibration sensors and all sorts of other devices. So what is piezoelectricity? It is, again, going back, piezo is a Greek word meaning stress, and electricity is electricity. So just from the word itself, what you can get is that you produce electricity with mechanical stress or strain. It is a phenomena that was discovered in late 1800s, and the way it works is, well, it's a reversible effect, so let me just put it that way. So what that means is that you can apply a mechanical stress or strain to a piece of piezoelectric material, and it produces electric charge, electricity. Or you can apply an electrical signal to the same piece of material, and it will change, it will deform mechanically. You will produce mechanical displacements or deformations using an electrical signal. For that reason, it is called to be self-generating, right? So if you have a piezoelectric sensor that is measuring a strain or stress, it is producing that charge without using an external power supply. Unlike capacitive devices or piezoresistive devices that we've seen so far, to measure the change in capacitance, remember you needed to have that DC voltage so that you could get a current out of it. To measure resistance, you have to push a resistance down the resistor to measure, let's say, the voltage variations. For a piezoelectric device, you just get a charge, or you just get a current if the stress is AC is changing. So it's called the self-generating effect, and that makes it desirable for low power applications where you may not have, let's say, the DC source or the energy source to, let's say, get the voltages or signals you need for proper piezoresistive or capacitive detection, or you do not have enough energy stored to use it for those kinds of measurements. The challenge is that the piezoelectric materials in general are not available in mainstream microfabrication technologies. Materials like aluminum nitride, zinc oxide, PZT, all these other types of good piezoelectric materials are not available at, or were not available in a typical MEMS foundry. Nowadays, people have found ways to integrate, especially aluminum nitride layers, into a lot of these different processes, and you can have access to those processes through different manufacturing facilities. But all in all, piezoelectric materials are not part of your typical microfabrication set of materials. Where do we use piezoelectricity at microscales? Well, you can use it to sense mechanical strain, because you get a current or a charge in response to mechanical strain. And you can use it as an actuator. You can apply a voltage to the piezoelectric actuator that you have and get a mechanical stress or displacement, if it is coupled to a structure, out of it. You can get almost any acoustic waveform that you want out of piezoelectric materials based on how you place your electrodes and then how you actuate them. In some cases, you can use piezoelectric materials for both sensing and actuation. So resonators are one example, and you saw one example in the electrostatic section, where you drive the device into resonance. At the same time, you want to monitor that and make sure that it is at resonance, it is operating at resonance. And piezoelectricity, because it is reversible, you can use it to force the structure into resonance. And once it is vibrating, again, you can use piezoelectricity to detect those vibrations. So what is it? Piezoelectricity in general happens because you have centers of charge in a material, and then you displace these centers of charge. So if you look at SiO2 as a piezoelectric material, SiO2 we're talking about crystalline SiO2 or quartz. It's better known as quartz. This is not the SiO2 film that we deposit through, let's say, CVD, or we grow from silicon through thermal oxidation. This is crystalline silicon dioxide. So if you have crystalline SiO2 because of the shape of the lattice of this material, you have, in this structure, you can see, for example, the lattice structure, you have oxygen atoms that will attract the electrons towards themselves, and silicon atoms that will give away their electrons. It's not ionic, it's covalent, but oxygens tend to hold on to the electrons more strongly than silicon does. And because of the way the crystal is formed, the center, if you look at the center of charges for the negative charges, it's going to be around here, for example, in this diagram. The middle of that triangle with 3 oxygens on the sides. And the center of charges for positive charges also happens to be at the same location, right? So an undisturbed crystal will have both center of positive and negative charges on the same location. Now, if you go and apply a force to this structure such that you deform the crystal a little bit, then in this case, let's say you apply the force to the sides of this, and what happens is that you push the oxygens a little bit to the top and silicons, let's say, a little bit to the bottom, towards the bottom. The center of positive charges will move a little bit downwards, and the center of negative charges will move a little bit upwards, right? So these are the charges inside the material. If you put 2 electrodes at the top and bottom of this piece of material, the negative charges at the top will attract positive charges to the top electrode, and then the positive charges at the bottom here will attract negative charges, equal amount of negative charges to the bottom electrode, right? And, well, moving charge to an electrode going in and out is current. That charge that you're accumulating on that top electrode or bottom electrode is measurable. You can measure it using a fairly simple electronic circuit, and therefore you can figure out how much force was applied to this structure. And then, the opposite happens if you stretch the material. So if you stretch the material, in this case, the center of negative charges moves downwards, the center of positive charges moves upwards. You get negative charges on the top electrode and positive charges on the bottom electrode. And again, you can figure out, if the force was compressive or tensile that way. The typical piezoelectric materials are listed here. Quartz, of course, is a crystalline material, so you cannot really deposit it on silicon. You do not have the right starting seed layers for that. You can bond some, not all, but you can bond some piezoelectric wafers to silicon, but the thermal mismatch issues are going to be a problem in most cases. If you're growing a film, or if you're depositing a film on your silicon substrate, your choices of materials are usually limited to aluminum nitride, zinc oxide, or PZT. PVDF is an interesting material here. It's a polymer that has piezoelectric properties, and that makes it an attractive choice for example, cases that you want to make flexible piezoelectric sensors and actuators. Bendable, for example, right? So how do piezoelectric transducers work? Well, the relationship between the charge and strain is given by the expression shown over there. So the piezoelectric property says that if you apply a mechanical stress sigma to a piece of piezoelectric material, you get a charge density of pp on the surface of this. And these two are related through that piezoelectric coefficient D. Charge density is coulombs per square meters, and stress is newtons per square meters. If you want, you can just, instead of normalizing it by area, you can say the amount of charge that is produced is proportional to D times the force that you're applying to this piece of piezoelectric material. So the reverse piezoelectric effect, where you produce a strain in response to a voltage, is formulated similarly. So in this case, what you have is a strain in response to your electrical signal, electric field, right? So a mechanical strain in this case is D, your piezoelectric coefficient, which is actually the same as the one that we are using in the above, times electric field. And in this case, if you want to use a voltage instead of, let's say, electric field, you can multiply both sides by the initial thickness of the material and get the voltage at the output. And the overall stress-strain relationship for this piezoelectric material will now become something like this, where S is your compliance or stiffness coefficients, so you get the typical response of an elastic material. The strain is proportional to stress. So S is from your compliance matrix, right? Converting a stress to strain. And then you have this contribution from electric field. The last term in there, D times E is electric field. And of course, because you are dealing with crystalline materials, everything is going to be direction dependent, right? So you have these coefficients that, or these indices that indicate, for different directions what's going to happen depending on, the direction that you apply the field or you apply the stress. And we'll talk about that very briefly. So things you usually have to deal with matrices in a crystalline form, and as usual, we try to make our lives easier and focus on cases that are more practical than purely theoretical. So we focus on special cases, not the most general situations. Now, one more thing I forgot to mention here is that, remember we have a charge here produced in proportion to the stress you apply. And then you have charge on these two electrodes separated by dielectric material. So you have a capacitor. If you want to know how much voltage you will have between these two electrodes, all you need to do is divide that this charge by the capacitance between these two electrodes. So if you want to calculate the voltage, you go and calculate the amount of charge first, you know the capacitance, and divide the charge by the amount of capacitance to get the voltage across the electrodes. Coming back to here, you can see that the strain you get is again a combination of what you have from stress and electric field. In general, the piezoelectric effect increases the stiffness of the material. The reason for that is that, or the apparent stiffness of the material. The reason for that is that you apply a stress to this structure, you produce internal charges in the, or you displace the centers of positive and negative charges inside this structure, you produce an internal electric field. That electric field is going to produce a mechanical displacement, which is actually opposing the initial displacement you produced. So the material appears to be stiffer than what it actually is because of the piezoelectric effect. And on the electrical side, the piezoelectric effect, what it does is that it makes the dielectric constant of the material appear larger than what it actually is. So for most piezoelectric materials, you see a very large dielectric constant because of this polarization issue. Now, in MEMS situations, again, we are focusing on relatively simple cases. You usually have two parallel electrodes and a piezoelectric layer is sandwiched between the two electrodes. We usually take advantage of only two possible modes for the piezoelectric actuation. They're known as 3-3 and 3-1 modes, named after the three axes that you have, the Cartesian axis that you have, 1, 2, 3 for, let's say, X, Y, and Z. In the D3-3 mode, the direction of stresses and strains that you're considering or you're looking at is the same as the direction of the electric field. So for the diagram shown here, you apply the voltage between the top and bottom electrodes. The electric field goes vertically from the top electrode to the bottom electrode. And you're also looking at the displacements along the same axis, along the thickness, let's say, of this, or the gap between the two electrodes. So this is called the D3-3 mode, right? So the change in the thickness or the strain that you get in the vertical direction is proportional to the field in that same direction times the D3-3 coefficient. Another possibility is the 3-1 mode, where you again apply a voltage between the top and bottom electrodes, but in this case you look at the changes in dimensions, let's say in X direction or in Y direction. Usually it is symmetric. So in D31 mode, you're looking at the lateral deformations due to a vertical field applied to the piezoelectric material. And again, the situation is similar. The lateral changes, the lateral strains are proportional to the field that you apply normally times the D31 coefficient. Typically, the 3-1 mode is the one that we use more often. And the simple reason for that is that we normally have the materials that we deposit and fabricate in MEMS, you stack them on top of each other. So normally, in most situations, your electrodes are, let's say the bottom electrode is really at the bottom of this material stack. Then you have the piezoelectric layer and then the electrode, top electrode on top of that. So your field is almost always normal to the direction of the wafer. But in most situations, the displacements that you want or you intend to get are in plane of the wafer. And to do that, you usually, you have to utilize the 3-1 mode. You always get the 3-3 as well, right? So the material that has a D31 will have a D33 as well. But what I mean here is that you do not really take that into account, or you just focus on the 3-1 aspect and then use that. Nonetheless, both of them are available to you. There are devices that actually benefit from the 3-3 mode to create vertical motions. Now, here is an example. What we have in this case is a piezoelectric resonator. What we have is a sandwich of two electrodes and a piezoelectric material in between. The device dimensions are given, and there are three parts to the problem. The first part is we want to calculate the stress due to a applied voltage between the two electrodes. The second part is that, what is the displacement if we operate this device at its resonance, and we have the value for resonance. And then the last part is that we assume that, so for some reason the device is operating or vibrating at its resonant frequency for whatever amplitude of motion that we just calculated in the above, and we want to see how much voltage is produced, right? So we're looking in the first two parts, we are looking at using this piezoelectric layer for actuation. Last part, we're going to use it for sensing. But the structure in all cases is going to be the same. So, okay, so let me quickly draw the cross section, let's say. Right, so top electrode, let's say this is electrode at the bottom, electrode at the top, and this is the piezoelectric material. The thickness of this layer is 1 micrometer. The length is 100 micrometer, and the width in that direction is 60 micrometer. Okay? The Young's modulus for the material is given to be 190 gigapascals. We are interested in the in the bulk extensional mode of the vibration. In this vibration mode, the device becomes longer and shorter, right? So in that linearly, across that longer dimension, it becomes longer and shorter. My field is between these two. So I'm interested in D31 in this case. D33 value is given, but D31 is the one that is going to basically operate the device at the mode that I want. It's 2 picometers per volt. The relative dielectric constant is given to be 100. And part A is what is the strain due to VDC equal 1 volt applied to this structure. Okay, so it's a DC voltage, we get a DC elongation of this structure due to that field. So if you want to do the calculations, you can show that the strain is D31 times the electric field, vertical electric field, which is your V in divided by the thickness of the piezo material. So let's just call it TP, right? And D31 is 2 picometers times 10 to the minus 12 times voltage is 1 volt divided by 1 micrometer for the thickness. So this is going to be 2 times 10 to the minus... The strain is going to be 2 times 10 to the minus 6, okay? So meters per meter or micrometers per micrometers. 2 ppm basically. This is a tiny amount of strain. Normally we cannot measure it, it's just too small. So at DC, I really don't get that much out of this system or out of this device. Part B of the problem says, what is the displacement at resonance for the same device? So what is the displacement at resonance? And we are told that the resonant frequency is 10 megahertz and quality factor is 10 to the 4. Okay? Okay, so what I can do is that I can say my AC voltage amplitude is VAC amplitude, has 1 volt amplitude. So the strain I should get off resonance should be the same as what I'm getting with DC. So I'm going to use that strain that I calculated before. But at resonance, everything is multiplied by Q. So the strain at resonance, let's say epsilon resonance, is going to be Q times epsilon DC. And this is my strain at DC. So quickly I can see that it's going to be 2 times 10 to the minus 6. Q is 10 to the 4 for this device. So this is going to be 0.02. That's 2% strain. That's actually a large amount of strain. Usually you shouldn't really get that much, but that's 2% strain. The length is, the relative change in length is 2%. So meaning that delta L over L is 2%, or 0.02. And for a length of 100 microns, you can show that delta L therefore is 2 micrometers. So at resonance, this device is becoming 2 microns longer and shrinking by the same factor, right? So that's the amplitude of motion. So it goes up to 102, come back to 98. That's a lot of motion, right? But we get that range of motion because at resonance, you know, the same force that you had before gives you Q times more effort, Q times more output. The last part of the question says, okay, so let's assume that we bring this device under resonance somehow. And this is moving by the amount that we calculated in the above, or the strain that is calculated in the above. What is the voltage that would appear across those electrodes? If we make it vibrate somehow at its resonance, what is the voltage that will appear across the electrodes? So I'm going to just write under 2% strain at resonance. Okay, so in this case, What I can say is that, okay, I'll go back to the equations that I have. I can say that Q is dF, okay, and D is my D31 coefficient in this case. So Q on the surface is D31 times the force. This force I calculated, so it's going to be D31 times the electrode area, so WL, times the stress that I have. The stress I calculated from Young's modulus times the strain. Right? So this is the stress, this is the force, and then I have everything that I needed. If I go and do the math, you can show that the charge is going to be let's just do the calculation here. So that's 2 times 10 to the minus 12 times 100 times 60 times 10 to the minus 12 for the 2 microns that I have here, times 190 gigapascals for the Young's modulus, times the strain that I have, 0.02 times 0.02, and therefore you can calculate the charge to be the charge is going to be 45.6 picocoulomb. Sounds like a small amount of charge, but let's see what is the capacitance, because if I want to calculate the voltage across the electrodes, the charge has to be divided by the capacitance, right? So the capacitance is the relative permittivity times the permittivity of free space times the area of the electrodes divided by the gap between them. And in this case, the gap is the thickness of the piezoelectric layer squared. So if I go and do the calculations here, I see that sorry, just not squared, just the thickness. It's going to be 5.3 picofarads, so that's the capacitance. And putting these two together, I can see that the voltage appearing across this device is going to be .6 volts at 10 megahertz, of course, right? Because this is operating at its resonant frequency. 8.6 volts is a huge, huge, huge signal if you're doing any kind of a sensing measurement. You know, you shouldn't really have any complaints if you get anything above a few millivolts. So 8.6 volts is huge. Nonetheless, this is an example, like real life always provides additional challenges to you. Okay. So moving forward, the design with piezoelectric layers, well, there is tons of advantages. You get large output signals, as we just saw. The transduction mechanism is linear over a very large range of displacements and input electric fields, unlike electrostatic actuation. The coupling between the mechanical domain and electrical domain is stronger. As you saw, you get very strong signal due to relatively small displacement, we actually like that and use it for energy harvesters, right? So the strong coupling of energy between mechanical and electrical domain means that if you attach a piezoelectric layer properly to a mechanical mass spring system, if you have vibrations in the environment, this thing is going to go up and down, and with a piezoelectric transducer somewhere, you can efficiently convert those vibrations into electrical signals or electrical energy that you can use for something else. So that's how vibration energy harvesters, most of them, work anyway. You can employ and excite almost all of the major vibration modes using piezoelectric transduction, and part of it is because the transduction goes into the material and you're basically producing body forces here. Electrostatic actuation, on the other hand, applies to the surface of the device. So you really do not have access to inside the material. And once you have access to material inside the device, you can actually excite some interesting vibration modes like surface acoustic waves. The device is stiff. It is good for rugged use. You don't really have those combs that can get particles in them and damage your operating conditions. Self-generating, so you can run them for continuously. But there are disadvantages. And the major one for piezoelectric transduction is that you have to have an AC signal. It has to be vibrations. You cannot really look at them to measure a constant force. The reason for that is that you apply a constant force to this electrode, you produce charges on the two electrodes of this capacitor. That's all good, but the problem in real life is that there's always leakage mechanisms. So you produce that charge, and we saw that it doesn't have to be a large amount of charge, like 40 picocoulombs of charge. And if you have any sort of charge leakage mechanism here, that charge will disappear fairly quickly. So piezoelectric transduction in general is not good for DC sensing. For AC sensing, if instead of a DC acceleration you want to measure vibrations, that's an excellent choice. The materials for piezoelectric transduction are not standard microfabrication materials. As I said, there is a growing number of foundries that provide access to these materials, but still relatively niche. And the issue that you will have with piezoelectric transduction is that you have to actually know more about your parasitics. Because the method itself, the transduction itself, is fairly linear, but the parasitics that you may have around may not be linear. So you may see some nonlinearity in the operation, which comes from the parasitics and not the device itself. So these are some of the vibration modes that you can excite using piezoelectric transducers. I'll show you the QCM, the quartz crystal microbalance one in a second, but in this case I have one electrode at the top, one electrode at the bottom, and the vibration mode is such that these two electrodes actually move like this across the piezoelectric layer, as you can see here. But there's all sorts of other vibration modes, as you can see in this slide. The QCM that we just mentioned looks like this. So you have the quartz crystal between two electrodes at the top and bottom. Quartz is SiO2, is glass, it's transparent, as you can see. And the application of these QCMs, or in this particular case, is for mass sensing. So what happens is that you take this device, you make it resonate at its resonance frequency, and now if you have some mass sitting on the top surface, it increases your effective mass. Your stiffness comes from the crystal itself, but the mass can increase because of what accumulates on the surface, and it is very, very sensitive to that changes in mass. You can weigh single bacteria using these techniques, and in our lab we've used similar devices to measure less than nanogram of change in mass on the surface. A SAW device, a SAW resonator, is an interesting device. In this case, you again have resonance, but the property of the wave is such that the wave energy is within a very short distance from the surface of the material. It doesn't penetrate deep into the material. So what you can do is that you can take this piece of piezoelectric material, put it inside a package. You don't really care too much, or you shouldn't be as sensitive to the mounting at the bottom of the material, because all of the energy for the wave will be at the center or at the top of that material layer. And SAW devices were used for mechanical filtering of RF signals for a long time. They are now replaced by a different type of resonators that look like this. These are called bulk acoustic resonators. And in this case, the device I'm showing you here, it has a piezoelectric layer on top of a piece of silicon. I excite it in that extensional mode that we just solved the problem for. And I use silicon over there for mechanical support, for getting a higher Q, but all the actuation comes from the piezoelectric layer that I have on the top. And these are the typical responses for the piezoelectric resonators that I mentioned. And then once more, I want to show you one device that we've made at SFU. It's a piezoelectric vibration sensor. What we're doing here is that we have a layer of piezoelectric material on the top of the wafer. We keep a portion of the substrate behind the membrane, so that acts as a proof mass for us. The membrane itself will be our spring. And now when you have vibrations in the environment, this goes up and down, and you produce stresses and strains on the piezoelectric layers. They're underneath these electrodes. You cannot see them, they're under the electrodes. But then we have the electrodes here to collect that charge and measure it. This device, this chip, is about 9 millimeters by 9 millimeters, and you already can see that we have tens of these devices made here on this tiny chip. These are fantastic vibration sensors, again, some of the best out there, with a noise level that is essentially limited by the electronics. So as you can see, this is the noise from the device itself, this is the noise from the electronics, and that's the challenge we have here, to choose a circuit that is more performs better, has less noise, so that we can do better in terms of detecting small signals. And finally, here is a probe where you have a piezo layer here. This is an AFM probe. We talked about this early on in the course. The probe goes across the surface, and if you have roughness on the surface, it goes up and down in response to that roughness. What you need to do is to measure how far this probe has gone up and down, and then by rastering the surface, you can basically map the roughnesses on that surface. Normally, this is done with an optical setup. You shine a beam of laser to the back of this probe, and you move. You look at the movements of that beam of light, or that spot of light on the sensor. But with a piezoelectric actuator, well, again, you have an AC signal, right? This is going up and down. You're not tracking the roughnesses on the surface. You can actually get rid of that optical setup. In this case, in this particular case, the piezoelectric actuators, the sensors, actually piezoelectric transducers could actually be used to move the probe as well. So you can actually follow the roughness on the surface using the piezoelectric actuators if desired. So that's that for the piezoelectric transduction mechanism. We have a couple more that we'll cover in the next lecture, and that will conclude our discussion on transduction mechanisms for microsystems. And I'll see you soon. Thank you.